Hi guys, welcome to my channel and I am going to be explaining you DQN, and its main purpose is that given enough time the computer will have the ability to master any game or simulation. When I talk about environment, it basically means a game, and for me, I just built a game Pong, the retro game Pong, so that's my environment. The states is the game variables or pixel data from the environment. Basically, the states are like the input for neural network. Let's add that in. The input for the neural network. Now, the action is fairly simple. It's basically the neural network output, given the states or input. And reward is a scalar number representing how well the action was took. And for example, let's just say our reward is -1, and that means typically that it should not do this action. And if our reward is -1, we will tell to our simulator or to our agent or computer that we should not do this action. It's wrong. The reason being is because it does something that's bad for the environment or like the game. For example, a reward could be -1 if a paddle or no, like a player misses a ball. And in my case, my reward will be -3 because my player did not receive the ball back to its enemy. +1 means it should do this action. And for example, in my game, it will be like if the player actually hit the ball and not put it back, but gave it to the enemy. Oh yeah, and by the way, my game, the enemy is basically invincible. I just want to see if my implementation is correct. DQ networks or DQN actually uses neural networks in order to train. So we will be just doing a brief introduction to neural networks. It's a very simplified one, but if you really want to learn more, I highly recommend you to watch 3 Blue, 1 Brown neural network series. That's how I learned from him. That's how I learned neural networks, and he is great at explaining neural networks. But this is a simplified version, so without further ado, let's go on. So there's two algorithms for neural networks. There's the predicting, so predict, and there's another one. It's called backpropagation. Propagation, yeah. It's like shortly known as backprop. So first we're going to go over predicting. So we have these inputs. Let's just say some arbitrary number like 0.05 and 0.6. Okay, and we have these weights, and again these are arbitrary. 6, 7, 0.23. Okay, so using these inputs and these weights, we get a new value or number. And again, this is completely arbitrary. This value or this number has nothing to do with any of these numbers. But if you learn 3 Blue, 1 Brown neural network series, you'll learn the relationship between both. And yeah, that's just predicting. You're taking numbers, basically, and you have these weights, and then you're getting a new number. Now backpropagation. So this is where the learning part comes in. So first we have two inputs, and we also have a desired output. Let's say we want the desired output to be 0. So if our desired output is 0, then what we're saying is basically we want the output to become 0. So it does some more calculations in order to edit or change these values. Now this value can be like 0.2, or probably this could be 0.4, and slowly but surely, after you give it enough training data, you get to a value of 0. And what I mean by training data is a input, output, and a desired output. I mean, like these two are inputs, input, and a desired output. Sorry. And yeah, that's just the basics of neural networks. Again, I highly recommend you if you want to learn more about neural networks through Blue One Brown Neural Network series. Okay, so this is my evidence. You could see that my agent got a max score of 114, and it was just currently getting a score of 29 until I actually stopped it. But after 803 episodes, it got a max score of 114, which I think it's good. The episodes what episodes are is basically how much times the agent has failed to retrieve the ball. So yeah, that just counts by one. And yeah, that's the max score. Okay, so now on with the algorithm. So I'll pull this up in the DQN paper. I'll link it down in the description below. But I'm just going to go over each line and try to simplify it for you. That way you'll be able to learn what the DQN algorithm really is doing. So first, initializing replay memory with capacity n. We're not really going to worry about that now, because the reason being is because there's a lot of, when we go over here into this subsection, let's just say, that subsection, then we'll be able to learn more about replay memory. So anyways, just on to the next one. Action value function Q with random weights. And you could already tell by the looks of things by saying weights that these two are neural networks. Initialize target action value function. Q is a caret, I guess, and then it has a weight. And you just set them equal to each other. And then. So then this initialize sequence n, this is basically getting your, I'm going to do it in text this time. It's basically getting your current state from your environment. It's basically getting your current state. So let me just edit that real quick. Getting the current state. Okay, so now with probability this, and then select random action A. Okay, so for this, this probability is actually dependent on an equation. It is described in the DQN paper, but this is just basically my equation. So 1 means that the probability will be 100%, and 0.1 meaning that it's going to be 10% probability. So then this x value is actually going to be calculated in frames. So every time it iterates, every time the agent trains, this frames will go increment by 1. And eventually, once it hits 1000 frames, it will just be flatlined and it will just be constant for 0.1. So yeah, that's the probability. So once you have the equation and you have the frames, you can find out the probability. And all you have to do is just execute that probability. Now what I mean about executing probability, if I go over here and I say C++ executing, or like just say C++ probability in general, there should be random numbers with different probabilities. It's simple like this. So just try to read this. Just read this answer, and it's a good explanation. So once you find that if it's true or false, if it's true, then select a random action. If it's false, then you do this equation. And actually, this equation may look overwhelming, but it's actually really simple. All it is really is just, if I go over here, all it really is just argmax, or let's just say A for action. So argmax, net, or just say, let's say net, and net is basically the action value function, and then current state. That's why we needed that, getting our current state, so we could use you could use that for our action. And yeah, that's basically other than that. Now include action A in emulator. Now what that really does is basically that it updates the game variables according to your action A, and that action A must be given or is given from our neural network or from our random action. Now observe reward R. Reward is actually given from our environment, and like we said before, reward is a scalar, like a scalar. Let's call it a number. Is a scalar number that depends on the action, and it gives out how good it is, like how good the action was taken. I don't know. And then the image plus x plus 1, I'm actually going to rename this. This is basically called next state. If you look at my GitHub program, this is actually basically next state. And that's basically, that is just basically the state after the action was took. And yeah. Oh, okay. Said this to this a pre-process. Okay, I do not entirely know what this is. I just skipped it. So I'm just gonna do outline. It's called. Is there red? I guess it's a good red color. And I'm gonna do this. Yeah, because I do not really know what that is. So yeah. Okay, so now store transition, state, action, reward, and next state. And you can notice that this is D, representing that our replay memory. Now, so in simplest terms, I just want to explain the capacity part. So if we have, in simple terms, like if we have an array of capacity, with a capacity, if we have an array with a capacity, and the array contains like a set of elements, like for example this, and we want to append the number 6, what we do is that we delete this number and then we append this to the top. So then the new number or the new array will be 3, 5, 3, and 6. Notice how these shift over there. So yeah, that's what's its capacity. If I just do that, oops, and that's the capacity. And instead of those numbers, it's actually storing a vector or an array of a state, action, reward, and a next state. Okay, so now we're going to do sample random mini batches of transition over here, and hopefully it should return a state, a action, a reward, and a next state. So you could first see the word mini batch, meaning that we're gonna do this multiple times. Hopefully I could be able to draw a straight line. So our mini batch is basically a parameter, and our mini batch size will be 32. That is my mini batch size. You could alter it, but yeah, my mini batch size is 32. So meaning that so like it iterates for 32 times, you just get a random transition from the replay memory. With that random transition, you get a state, an action, a reward, and a next state. So now let's go to this over here, where this is like an equation. Okay, so you may be wondering, what is this? If episode terminates at step J plus 1. Now, what that does, so, okay, let's just say in my environment, in my ping pong game, the episode will terminate if the ball goes over here, but like ball just goes over here, but then the player just goes in the opposite direction of the paw, meaning that the player failed to retrieve the ball, and then the ball and the player and the enemy, the whole game will be reset. So therefore, since that the player failed to receive the ball, the episode will terminate. Else if it's in the air, not in the air per se, but if it's somewhere else, or like if it's in the enemy's place, then it will just calculate this. It'll just calculate this equation. And this equation is a reward. So I think you could look. R just stands for reward, and you could find this symbol, which is gamma, and that gamma is basically 0.99. Then max target value, target function, the next state. So really, I'm actually gonna do code wise. Y is equal to reward plus 0.99 times max target net predict next state, and yeah. And yeah, that's just. Oh, I forgot to mention max and argmax. Yeah. So what that is basically is, so suppose we have a array of like 5, 4, 3, 70, all this. These are completely arbitrary numbers. So yeah. Oh, whoops! I have to charge this. Yeah, I have to charge this real soon. I have to charge my Chromebook. But yeah, so if you want to find the argmax of this array, what we have to do is find the max value, which is 75, and then just try to get the index of it. So the index will be 0, 1, 2, 3, 4. And since the highest number is 75, we could say that the index is 3. So this argmax will return a value of 3. However, if we're doing max, then we're not going to look at the index. All we have to do is just find the max value and then return it. In this case, it will be 75. So that's max value. Now performing gradient descent. Perform gradient descent on my, okay, wait. Perform gradient descent on this with respect to network parameters. I'm gonna try to explain this the best as I could, but again, if you need any, if you have any questions, feel free to put it down in the comments below. But anyways, performing a gradient descent, right? So first, let me just write it down in code format. Basically, like the code that I would write. So we have this target, and then yeah, it's just pretty self-explanatory. Oh, you know what? Let me try to give up let's try to provide an example. So for example, let's say our target value is 0.52, 0.92, and then not 2, let's just say 1, 0.21. Okay. So this is our target. Let's just pretend that this array is our target, and let's say our action is 0, 1. The reason because this is the highest value. And so let's say it's y, and in order to get y, let's say that the episode terminated and the reward was -3. So, meaning that we say that target action is equal to y. What this basically does is that it replaces 0.91 with y, and in this case it will be -1. I said a reward of -1, then it will replace it with -1. So, and then it backprops it backpropagation. I think you hopefully knew that with my short demonstration of neural networks. But yeah, and now this is the desired output. And so, since it will be learning to train that this is the desired output, and hopefully when this comes again, or like when this similar state comes again, then then it will hopefully choose another action. Like for example 0, because since -1 is not very high, but 0.52 is high compared to the other values. Again, that is just my interpretation of it. Like at least I did it and it works. I had to do some research. Just please let me know if it's confusing. I'll try to sprinkle it up. Or like try to not sprinkle it up. Try to explain better. Anyways, now on to the next one. Every C step resets this and this. For me, my hyperparameter for C will be every C. I think it's equal to every 1,000 frames. So yeah, just keep that in mind. And all you have to do is just say, well, in code wise, target network is equal to network. That will just for me that will set the weights and the layout and basically everything. And yeah, that's the end of our algorithm. Again, if you have any questions, put it down below. Thank you for watching, and I will see you in the next video. Bye.